All right, so we've been talking about acceleration. Okay, we've been talking about position and time, velocity versus time graphs. Okay, all of that kind of builds to work and energy. Now, what we're going to go over today and for the next week or so is, without exception, the most important concept in all of science. And I don't just say that because I'm a physics guy. Okay, if it wasn't for energy, nothing would happen. All right. What we have to look at is, how do you get energy? Okay? How can you transfer energy to something else? Both of those involve work. Okay? So we've got to be able to do work, okay, to give energy to something else, but in order to have energy ourselves and be able to do work, something has to give energy to us. Now, obviously our body converts chemical energy in our food, okay, into potential chemical energy in our muscles, which can then turn that into mechanical energy. Okay? That's where we get our energy from. It's not that something does work on us so we can do work on something else. It's not as simple as that. Okay? We are going to simplify it a bit, okay, so it is a little more like that, but that's what we're going to be looking at, is how do we transfer energy to something else? How do we give something more energy? Or how can we take energy away from something? All of that has to do with work energy theorem. Okay? So if you do work, work is going to change the energy of something. Okay? That's what work is. Work is a change or a transfer of energy. You might want to write that down. That's kind of an important thing. Okay? Work is a change in energy. Okay? That could mean that it involves a transfer of energy. Okay? A transfer to or a transfer away. So in that regard, work can be positive or negative. It's not vector, okay, which is going to seem weird because everything else we've dealt with that's positive or negative has been a vector quantity. Work is not. Okay? But it's positive or negative based on whether you're gaining energy or losing energy. Okay? If something does work on me, from my point of view, that's positive work because my energy goes up. If I do work on something else, from my point of view, that's negative work because I'm transferring energy away. Does that sort of make sense? Okay? But it's not a matter of, I did 200 joules worth of work north. I can't do work in a particular direction. When I transfer energy to another object, it gains energy. It can do whatever it wants with it. Okay? Therefore, it can't have direction. Otherwise, every time you ate something, you would have to give a vector on where that energy went. For me, it's usually right here. Okay? I don't know what vector that is, but it's not applicable to me in any way. Okay? So work and energy are both scalar quantities. You either have some or you don't. Okay? Or you have a little bit. Okay? But you don't have energy with direction. Everyone all right with that? Okay. All right. So work and energy can be equal. Okay, but one can't exist without the other. It's one of those chicken and the egg arguments. I have energy because something did work, but I can't do any work unless I have energy. It's like back and forth, back and forth. Okay, understand kinetic and potential energy. Right? Kinetic energy is energy that you have if you are doing what? What do you have to be doing to have kinetic energy? Moving, yeah. Kinetic energy is energy of movement. Okay? Potential energy, at least from a mechanical energy standpoint, is energy due to your position or condition. Okay? So right now, the hole punch over here on the table has potential energy. Because it's where? Yeah, it's on top of the table. It's above the ground. It could fall if I pushed it off. Okay? So therefore, its position gives it gravitational potential energy. Right? If I had a slingshot and I had pulled it back and had a rock in there, not that I would do that to anybody, okay? But I have a rock in a slingshot, I've pulled it back. Does it have potential energy? Yes, because of its condition. It has been put into a device that contains elastic potential energy. If I let it go, okay, it's going to fly out. Why? Where did that potential energy come from? Okay, how did the elastic get it? Because I pulled it. Exactly. Okay? The elastic got energy in it because I did work on the elastic in changing its shape. That is, I exerted a force on the elastic through a distance. That's what work can be. Work can be calculated that way. If you take the force you exert, you multiply it by the distance over which you exert the force, and you can calculate how much work you've done. Okay? A bow and arrow, a slingshot, or any of those kind of things are prime examples of that. Okay? Converting one form of energy to another. Okay? So let's say that in that slingshot example, let's say that I do 150 joules worth of work in pulling back the rubber band. When I let it go, how much energy will the rock have? I did 150 joules worth of work. I let the slingshot go. How much energy will the rock have when it leaves the slingshot? 150. Now, in the perfect physical world, that's how we're going to operate. In the real world, it's not going to be that. Okay? Why isn't it going to be that in the real world? Yeah, energy is lost to the surroundings. We talked about the surroundings in the system back at the start of the unit. Okay, when I release that rubber band or that slingshot, it makes a snapping sound. Sound's a form of energy. There's some of my work wasted. Okay, there's going to be some heat. Okay, in the rubber band when you stretch it and when you release it. Okay, all of those kind of things. There's going to be some air resistance on the way through. All of that stuff steals energy. Okay, we're going to deal with the perfect physical world where all the work I did got transferred to the rock. It would have 150 joules of energy then. Okay. All right, and the relationship between force and work. Well, according to this formula, if I exert more force, what should happen to work? It should increase. If this number gets bigger, this number should get bigger. Okay, same thing with D. If I exert the same force but over a longer distance, will I do more work? Yes. Okay, that's how it works. Okay. I mean, if you think about it from this perspective, if I lift that hole punch to the table, I do a certain amount of work. If I was to lift it and put it on top of the lock up there at the back, would that be more work? Yeah, it'd be the same force, but I'd lifted it higher. And as a result, it would have more energy, because I would rather it fell off of that table and hit my foot than off of the lock up and hit my foot. Because by the time it gets to the ground falling off the lock up, it's going a lot faster, okay? Because it's got more energy. Okay? So it's kind of, think about it always kind of in a common sense perspective if you can. Okay, so energy is a measurable quantity. We say measurable. I mean, you can't, there's not really a scale that measures energy, but okay, we can at least calculate it based on other measurable values. Okay, so specifically, energy is a measure of an object's or system's capacity to do work. That is an important definition. Okay, energy is a measure of an object or system's capacity to do work. Okay, and by the same token, work is a transfer of energy from one object or system to another. Okay, according to those definitions, if I have no energy, can I do any work? No. Work's a transfer of energy. If I don't have any, I can't give any away. Okay, everybody all right with that idea? All right, classic mousetrap. Perfect example of work energy theorem. How many people have ever loaded or set one of these before? Okay, so you set one of these by taking, these are the actual technical names, taking the killing bar, that's its job, okay, and bringing it back over from this position, okay, to the loaded position, and then locking it in with the locking bar. Okay. Now, when I have done that, is there energy in the mousetrap? Yes. Okay. There is potential energy stored in the spring because I've changed the shape of the spring. Okay. I exerted a force over a distance in pulling the killing bar back into the loaded position. Everybody all right with that? Okay. So it's got energy. If it is triggered, can it do work? What's the evidence we have that it does work? A dead mouse. I know I'm not trying to be cruel on that, okay? But it is going to change the shape of the mouse in an undesirable way, okay? For the mouse. For us, it's a desirable way, okay? But okay, when it snaps forward, it's going to convert all of the potential energy in the spring into kinetic energy of movement. It's going to move really, really fast, okay? And then it's going to stop suddenly, okay? And when it does that, something stopping it means that it's exerting a force over a distance on something else. It's doing work, transferring energy, okay, away. If there's no mouse in it and just snapped it with a ruler or something like that, you have evidence that it had energy because it, A, makes a really loud snapping sound, and it'll actually hop right off the ground, okay, if there's nothing in it. Right? All evidence that there was energy stored within the mousetrap. Okay? In fact, when I used to teach Science 24, we used to build carts that were powered by mousetraps. Okay, so you would put the mousetrap on the back and set it against the wall and trigger it, and it would shoot the cart across the floor. Okay, what's that? It doesn't really work all that well, but it's fun to do in Science 24. Okay, yeah. All right, everybody got that idea there? Okay, this is the relationship between work and energy. You got to have energy to do work. The only way you can have energy is for work to be done to you. Okay, that's the weird thing about that's the chicken and the egg kind of thing. All right. Another example of work energy theorem. If you hit a tennis ball with your racket, okay, the ball has work done on it because when we throw it up in the air, okay, it doesn't have a whole lot of energy, especially at the point where you hit it, because that's usually the spot where it's kind of stationary and changing direction. It's got a little gravitational potential energy, but it's not moving otherwise. Okay. Now, when I hit it, I exert a force on it over a distance, agreed? Through the racket, obviously. Okay? And as a result, the racket loses some energy. I mean, you can tell that if you've ever hit a tennis ball or any other kind of thing with a racket, you can feel the racket slow down as you make contact with the object, okay? In this case, the tennis ball. And you feel that impact. That is, it's slowing down because you're doing work. The energy is being transferred to the ball, which is speeding up. Okay? The idea here is that you can't create energy. You can't destroy it. Okay? You can transfer it around. You can convert it to other forms. Okay? But I can't give something energy for free. It's got to cost me, okay, when I do that. All right? Now, this whole idea of the work energy theorem is a big part of the science of sports. Okay? Everything that has been done to improve the ability of athletes to perform in sports, okay, has had to do, at least equipment-wise, okay, and sometimes technique-wise, with the work energy theorem. Right? This is a very old picture because this is a wooden tennis racket. Okay? Back in the day, tennis rackets were made out of chunks of tree, okay, not graphite and carbon fiber like they are now. Okay? And as a result, they were heavy. So, if I'm swinging a heavy old wooden racket versus a modern carbon fiber racket, which one can I swing faster? The modern carbon fiber racket. That means that if it's moving faster, I can probably impart more energy to the tennis ball, meaning I can serve it faster, hit it faster, okay, things like that. Everybody see what I mean there? Okay, what we're trying to do is take the kinetic energy of the racket and turn it into kinetic energy for the tennis ball. Okay, so the M here stands for mass. This stands for speed. V stands for speed. Okay, but speed is squared here. So the more important ingredient in hitting a ball fast or transferring lots of energy to it is how fast the racket is moving, not the mass of the racket. Okay, yes, if the racket is heavy, it'll mean it'll have more energy, but I can't swing it as fast. Okay, and speed is more important because it's squared. It's got an exponential relationship with energy, where mass is only linear. Okay, if I double the mass of my racket, and I can swing it just as fast, then I'll double the energy that the ball receives. But in reality, if I double the mass of the racket, it's going to slow the racket down, and I'm not going to have as much energy as I would have had with a lighter racket that I can swing faster. Okay, now in terms of technique, we go to this formula. Work is force times distance. Force generally has to do with strength. Okay? Athletes get stronger, they can exert more force. But if I can increase the distance over which I exert that force, I can also do more work. Okay? This is where technique comes in. Okay? If I am using, let's say, a modern like graphite or carbon fiber hockey stick, okay, those work way better than old school chunks of tree wooden hockey sticks like I had when I was a kid. Okay? Wooden sticks don't flex very much. So when you are shooting a puck with an older stick, okay, there's about a distance like this over which you can make contact with the puck and exert a force on it. Okay? Also, wooden sticks are heavier, so you don't swing them as fast. Okay? A modern carbon fiber stick, because it is flexible, increases the distance over which you are in contact with the puck. So given if it's the same person swinging both sticks, their strength is the same. Okay? The force they exert is the same no matter which stick they use, but the distance over which they can exert it is greater with a modern stick. Therefore, they shoot the puck faster with a modern stick. Okay? All sports come down to that. Okay? If you look like track and field throwing events, like Abby throws the javelin, okay? And we're always working on how much distance over which she can have her hand on the javelin, because the longer she can push on it, the farther she's going to throw it. Shot put's the same. Okay? How long you're exerting the force. Once you let it go, then that's it. You've done all the work you can do. Okay? Golf has a similar idea. Okay? Obviously, we have lighter clubs than we used to have. They're all made of graphite and lightweight titanium metals as opposed to big chunks of wood. Okay? So we can swing them faster. But the ball is also much more technologically advanced than it used to be. Ball used to be like hitting a rock. Okay, you'd hit a golf ball and it would vibrate in your hands and you'd hurt for a little while. Okay, now the ball is really soft, so that when you make contact with the club face, the ball actually squishes against it and flattens out, which means it stays in contact with the club face for a longer period of time. It's on the club face over a longer distance. You can hit it farther. Okay, everybody with me on that? Okay. The only sport that really hasn't embraced this, baseball. Okay, baseball still swings a chunk of wood at a piece of horse hide. Okay, it is not technologically advanced in any way, shape, or form. Baseball in that way is the same as it ever was. Okay, you can, but in the major leagues they don't use them, right? They only use wooden bats in the majors. So instead, they focused on the use of performance-enhancing drugs, which they have done an incredible job of. There are a lot of roid monkeys swinging bats in the major leagues. Okay, what does that change about this equation? The force. Yeah. Okay. If they're not going to let you change your equipment, unless you're Barry Bonds and you cork your bat, okay, which is also cheating. There's a lot of cheating in baseball. Okay. Okay. Unless you can cork your bat, okay, all you can do is work out and get bigger and stronger, so you can swing the bat faster. Okay. Now, if you cork your bat, does anyone know what I mean by corking your bat? You drill out the center of the bat and fill it with cork. Okay, so that it's lighter. There's drawbacks to that. You drill it too much, it'll break when you hit something, and you'll get caught, like Barry Bonds did. Okay, because it'll just shatter when you hit the ball. Okay, but a lighter bat, you can swing faster. Okay, so there is that idea, which is why there's a lot of regulations around size and weight of bats in the major leagues. Okay, to sort of eliminate that. Everybody follow me on that? Okay, so basically everything comes down to changing at least part of that equation so that we can improve how much energy we produce, okay, or how much energy we transfer. That's what work is, okay? The bigger W is, the bigger the energy of the object I'm working on is going to be, okay? And anything that can make that more efficient is obviously going to be better. All right, so that's the kind of the science of sports, okay, on that one. Okay, so work is also related, like we said, to the force acting on an object. The greater the force, the more work is done. We've already said that. Bow and arrow, slingshot, prime example. Okay, when I pull back on the string of a bow, okay, I am doing work because I'm exerting a force by pulling over a distance, however far I stretch it back. What am I doing to the bow itself? I'm bending it. I'm changing its shape. Anytime you change the shape of something, you've done work. Okay, when you were a kid and you played with Play-Doh, you squished it in your hand, you did work. You changed the shape of the Play-Doh. Play-Doh just doesn't bounce back. Okay, now with a bow and arrow, you're squeezing it. Actually, when you pull back, you're squeezing the ends closer together. The bow, whatever material it's made out of, wants to snap back to its original shape. Okay, and when you let it go, that's what it'll do, and it'll take all the work you did and turn it into kinetic energy for the arrow. in the perfect physical world. In the real world, obviously you hear the snap of the draw of the string and all of that stuff. Some of the energy is lost, but okay, we're going to deal again with the perfect physical world. So if I did 200 joules worth of work in drawing back the bow, the arrow will get 200 joules of kinetic energy when it leaves the bow. Okay? Now, what if, and not that you would do this, what if you aimed the bow and arrow straight up in the air? Okay? And there's no wind. Okay, so it can't blow the arrow around. Okay, and I release, so I pull it back, I do 200 joules worth of work. When it leaves the bow, the arrow is going to have 200 joules worth of kinetic energy. As it travels up, though, it's going to start slowing down. Is it losing energy? No. It's losing kinetic energy, but that kinetic energy is getting turned into potential energy. The higher it goes, the more potential energy it'll have. Remember, energy can't be created and it can't be destroyed. So as the thing goes up, it may lose kinetic because it's turning into potential. Okay? The higher up it goes, the more potential it'll have. At that highest point, where it's stopped for an instant, it has no kinetic energy and maximum potential. In the perfect physical world, it'll fall right back down. And when it comes back down, it should be going exactly the same speed it was when it left the arrow, or left the bow, sorry. Okay, that's in the perfect physical world. In the real world, that doesn't happen. Okay, because the arrow doesn't flip over and fall along its most aerodynamic dimension. It tumbles back down, and then it loses energy due to air resistance. Okay, but in the real world, if you fired a gun in the air or you fired a bow and arrow in the air, okay, sorry, in the perfect physical world, you'd best get out the way. Okay, because when it comes back down, it's going to be going just as fast. That's kind of law of conservation of energy. All right. Now, mass also affects the amount of work done, as a more massive object requires more energy to move. Okay? If you got a little kid's, little red wagon, it's pretty easy to push that because it's not very massive. Okay? But if you apply the same force to a dump truck, okay, you're going to do the same amount of work, but it's not going to look as impressive. Okay? You change the energy of the dump truck by the same amount you change the energy of the little red wagon, and the dump truck laughs at you. Okay? It's not going to move very much. It might rock back and forth or something. Okay? But that's about it. Okay? More massive things can have more energy if they're moving the same speed. Okay? If we go back to the little red wagon and dump truck example, you've got the little red wagon moving at 15 kilometers per hour barreling down on you, and a dump truck moving at 15 kilometers an hour barreling down on you, and you have to stand in front of one of them. Which one do you choose? The little red wagon. Okay, most of us would say that anyway. Okay, we stand in front of the little red wagon because it doesn't have as much energy. It's moving the same speed, but it's tiny. Okay, we'd be able to reach up, put our foot out, and stop it. Try that with a dump truck, and you're not gonna like what happens. Okay, it has way more energy, so it can do more work on you as a result. Okay, it has more energy to transfer to you because of its greater mass. Okay, mass, guys, is important. Okay? In Physics 20, we talk about this from an energy perspective as well as a forces perspective. Okay? In a car crash, there is a winner and a loser in every car crash. Okay? And the winner is always the car with more mass. Okay? Because it has more energy. Okay? And as a result, it will experience less acceleration than the lighter vehicle. Okay? That's why I drive a truck. Okay? I have little kids. Okay? If they're in the truck with me and I get in an accident, I want to win. Okay? It's defending my kids, and I'm really competitive. Okay? All right? And I say that I've been in a couple of car accidents. None of them my fault. Okay? But I have been, and every time I've been the winner. Okay? Yeah, I'm a little bit proud of that. Okay? All right? I had a lady who turned left in front of me in my, well, not the truck I drive now, but okay. And she turned left in front of me, and we were driving a big SUV. Okay, she was driving a little Ford Focus. Okay, and we were moving at about 60 kilometers an hour. Okay, not like overly fast, but when we hit her, okay, we moved her car backwards. We continued to move forwards. Cut into that little car like a hot knife through butter. Okay, ended up halfway into the engine compartment. Okay. Her airbags are off. She's turned around the other way. And I'm going, my neck hurts a little bit. My airbags didn't even go off. Okay? Because the acceleration I experienced was significantly less because of my greater mass. Okay? But it's true. Okay? It's true. Greater mass is going to end up good for you. Okay? Always. That's why, guys, like being on a motorcycle is so dangerous. There's no collision you can win on a motorcycle. Even a smart car has more mass than you. Okay? Well, but you're also not attached. Okay? That's the problem also with a motorcycle, is not being physically attached to it. Okay? Everybody follow me there? So mass is important. Speed's important too, but mass is also important when it comes to, okay, how much energy you have. All right. This is back to the idea we were just talking about. Okay, if this guy is using his golf club in the proper fashion, okay, that is to hit a golf ball with it, okay, he winds up and swings as hard as he can. He exerts a certain amount of force. He's hitting a very small mass, the golf ball. And as a result, he will produce a very large acceleration. This is Newton's second law. It is actually on your formula sheet. Force is mass times acceleration. Okay? So it'll produce a very large acceleration. That is, the ball will fly off of the club and go a long way. Okay? For some reason, he decides that a golf ball is too easy, so he's going to wind up and smoke this truck, okay, with his golf club. Now, he exerts the same amount of force on a very, very large mass, producing a very, very small acceleration. But here's the thing. In both situations, he does the same amount of work. Okay? He transfers the same amount of energy to the golf ball as he did to the truck. It's just the results are different. A very small acceleration means a very small change in velocity. But even that small change in velocity still means that the truck now has energy due to being hit by the golf club. Now, in the real world, is that truck going anywhere? No. Okay? Does that mean he didn't do any work? No. Okay? If I'm standing at the front of the truck and I have my hand on the truck, I know when he hits it. I can feel the vibration pass through the truck. That means every particle in that truck moved because it passed the vibration through to the front. Okay? I also know that he hits it because I'll hear it. Okay? There'll be a loud pinging sound or whatever a club would make when it destroys itself against the truck. Okay? All of that stuff would be evidence that work's been done because there's forms of energy now in the surroundings that I can detect. All right? So it doesn't necessarily mean the object has to move. Okay? As long as some parts of it move, work is still being done. Okay? Other evidence, there's probably going to be a dent at the back of the truck. Okay? That's change of shape. That counts as doing work. Okay? All of that counts. Everyone good with that? Okay. Okay, so that's what I just talked about here. Motion doesn't just mean the movement of the whole object. Okay? Yes, ideally in the perfect physical world, we'd like the whole object to move as one thing. Okay? But the reality of it is that all objects are made of atoms, the tiny little particles. And if we can make any of those move, it still counts as having done work. Okay? If we make a change in shape, that counts as doing work, especially to elastic objects like springs, bungee cords, elastic bands, okay? Things like that. It's because when we do work on them, the work we did is stored in them as potential energy. When we let them go, they'll snap back to their original shape, okay, and release that energy. All right. Okay, now, work and heat. We talked about this the first day, but this quick review. Work and heat are both transfers of energy, but the type of energy they transfer is different. Okay? Work is a transfer of mechanical energy. Okay? It's a transfer of mechanical energy. And mechanical energy is things like position, movement, shape. Okay? Whereas heat is a transfer of thermal energy. Okay? In what we're doing here right now, thermal energy is not going to be a concern for us. We recognize that anytime work is done, some energy is going to be lost to heat, transferred away as thermal energy. Okay, but we're going to imagine that it doesn't. Okay, just for simplicity's sake. All right, so they are similar in that they are both changes or transfers of energy, but they transfer different kinds of energy. And what we're dealing with right now is mechanical energy changes. Okay, that is, I do work on something so it goes faster, moves higher, or gains elastic potential energy, one of the three. Okay, I'm not worried about if I did work and the object got hotter. Okay, I'm not concerned with that. All right. potential energy. Okay? You have potential energy as long as you are not where? On the ground. Okay? You have to have the potential to fall to have potential, gravitational potential energy, that is. Okay? Gravitational potential energy is dependent on three things. Okay? This formula is also on your formula sheet. But gravitational potential energy is mass times the acceleration due to gravity, which is what number? 9.81, because we're only going to be dealing with these kind of questions on Earth. Okay? And the height the object is above the ground. Okay? Those three things can affect the amount of potential energy. Now, we say three things, but realistically, G doesn't change. At least not very much, okay, from place to place on Earth. So it essentially stays the same all the time. All right? But mass is a big deal. Okay? According to this formula, if I double the mass, what should happen to this? It should go up by how much? 2 times, right? It should double. It's a linear thing. If I have twice as much mass, I have twice as much potential energy, right? It would be like, you know, there's two things perched precariously on a building, okay? One is a piano, okay, and one is a pillow, right? I mean, which one would you rather have fall on you? They're going to fall from the same height. They're going to be going the same speed, okay, when they get down to the ground. Well, one's going to have less energy because it has less mass, okay? They fell from the same height, right? Now, I saw a few strange looks when I said they're going to be going the same speed when they get to the ground. Okay, I know in the real world it doesn't always work out that way, okay, but in the perfect physical world, all things fall at 9.81 meters per second squared. They accelerate at that rate, okay? The only reason feathers and pillows and things like that don't is because they catch the air and they have more air resistance, so they fall like this, okay? In the absence of air resistance, or if they're a streamlined object, they fall at exactly the same rate. Okay. And they've done this in places like they'll make a container and they'll vacuum out all the air so that it's a perfect vacuum inside, and then they'll drop two objects like a brick and a ping pong ball, and they fall at the same rate. Okay. Once you eliminate air resistance, everything, even a feather, okay, falls. In fact, you know what? I have a. All right. So kind of get the idea there. All things fall at the same rate. That's why we don't have a separate G for every object on Earth. Okay. But the things that potential energy is most related to are height and mass. Okay, yeah, obviously the higher up something is, the faster it's going to be going when it reaches the ground, so the more energy it must have had as a result of its height. Acceleration due to gravity. So G is going to always be 9.81 for us, right? All right. Yeah, and then we've got Wile E. Coyote here, if you've ever seen that, right? He doesn't fall until someone points out to him that he's not standing on anything anymore. Yeah, that's what we call Warner Brothers physics. Okay? It's not real physics. All right. So a couple of situations here. I've got this picture here on the left where I have a person lifting a block to the top of a ramp and a person pushing a block up the ramp to the top. Who does more work, assuming the blocks have the same mass? It's the same. Okay? When the blocks get to the top of the ramp, they are both the same height from the bottom of the ramp. They have the same mass, and gravity is the same. Therefore, it doesn't matter how you get the mass to the top of the ramp. You do the same amount of work. Now, again, that's in the perfect physical world where there's no friction to slide against going up the ramp. If there's a frictionless ramp, that's true. Okay? We haven't built any frictionless ramps, but that's the idea. Okay? That is, in fact, the whole idea behind the ramp. Okay? The ramp is the simplest machine. It's called the inclined plane. Right? If you don't understand how an inclined plane works, you will become an inclined plane wrapped around an axis. An inclined plane wrapped around an axis is a screw. You would be screwed. That's a Sheldon Cooper joke. If you don't watch the Big Bang Theory, it's like one of his best jokes. Okay, if you take a ramp and you turn it around an axis, it becomes a screw. That's why screws work. They're a ramp that goes down into a piece of wood. Okay, anyway, I hate it when jokes backfire. Okay, so the ramp is the simplest machine for this reason. It works on this idea. Work is force times distance. Okay, if I lift this block to the top of the ramp, I exert a large force over a small distance. If I push it up the ramp, I use a small force over a greater distance. In the end, I do the same amount of work regardless. No, it doesn't because you're multiplying them. Yeah. Okay. Does that sort of make sense to everybody? Okay, so it doesn't matter which way I get it to the top because it's going to change the force and change the distance. Smaller forces, bigger distances. Larger forces, smaller distances. I end up doing the same work regardless. Okay, this situation here, I've got a mass that's hanging and it's attached to another mass over a pulley. Okay, so if I lift this mass up so that it's 2 meters off the ground, have I done work? Okay, that energy then is all where? Which object now has all the energy from me? Okay, I take this ball and I lift it 2 meters above the ground, which by essentially sliding this one back. Okay, so I slide this one back, right? Which one is now holding all the energy from the work I did? This one. Okay, because it's off the ground. When I let this one go, when I let the box go, the ball falls and then pulls the box. But the box sitting here on the table isn't going anywhere, right? It isn't going anywhere until the gravitational potential energy in the ball does some work on it. Okay? Now, if I'm looking at it like individually, this one's got all the energy. Does the system have a lot of energy? Yeah. Okay? The whole system has got energy because I did work in pulling back and pulling up this ball. Right? Now, when this ball falls, its potential energy is going to turn into kinetic because it's going to speed up. But not all of it is going to turn into kinetic because some of it has to pull the block. Okay? So in this case, this thing is not going to fall at 9.81 meters per second squared because this is going to resist it. Okay? It's going to have to exert some force over this distance to do work in accelerating the block along the table. Okay? So this loses some energy. This gains some energy. But the energy of the whole system is going to stay the same. Okay? Each individual part can lose some, but the whole system has to keep the same number. Okay? Because I did work on the system. I pulled this thing back. I put energy into the system by doing work. That energy all has to be conserved. Not necessarily in one spot, but in the whole system. Okay? Everybody all right with that one? All right, so definition thing here, okay? This is important. Potential energy of an object due to its position, okay? All forms of energy must be described with respect to a chosen reference point. So when we're talking about gravitational potential energy, the most common reference point is the ground, right? We're going to measure their heights from the ground. That's the most common thing. Okay, if we're talking about elastic potential energy, it would be from the unstrained position of the object. If it's a spring, how long was the spring before I pushed the ends together or pulled the ends apart? Okay, that would be my reference. All right, so we talked about this already. You can calculate the gravitational potential energy of an object by multiplying mass times gravity times height. Okay. So EP is the gravitational potential energy of the object, and energy is, of course, always in joules. Okay, so you abbreviate that with J. Energy is always in joules. M is the object's mass in kilograms. In physics, we do things big. Okay, in chemistry, we use grams. Chemistry deals with atoms, they do things small. In physics, we go big. Okay, so we always use kilograms for mass in physics. Okay, G is the acceleration due to gravity. We know what that is, 9.81 meters per second squared. Okay, and H has to be the height, and that has to be in meters. Okay, the reason the units that we're so sticky on the units is because joules really are a kilogram meter squared per second squared. Aren't you glad we use joules? Okay, but that's what a joule stands for. Therefore, I have to use mass in kilograms, distance in meters. Okay, otherwise I would get thousandths of a joule or hundredths of a joule. It wouldn't be joules. Okay, if I wasn't using those units. You might just want to write that. That's the units for a joule. Kilogram meters squared per second squared. Okay, where do we get this from? work's force times distance. Okay, now force is measured, this is going to be a weird one, force is measured in newtons. Okay, and a newton is a kilogram meter per second squared. And I'm multiplying that by, what are the units for distance? Meters. Kilogram meters squared per second squared. That's where I get that from. Okay? You're basically never going to see these. I'll always use newtons for force and joules for energy. Okay? I'll never say it has this many kilogram meters squared per second squared worth of energy, because it just doesn't make sense. All right, so let's try this example here. First, it's already solved there, but we'll just walk through it. Okay, a 3 kilogram box is lifted by an upward force to 1.5 meters above the Earth's surface to the top of a table. Okay, what's the potential energy of the box in its new position? All right, well, I calculate potential energy by going mass times gravity times height. Mass of the box was 3 kilograms. Acceleration due to gravity is 9.81. The height I lifted it to is 1.5 meters. If I multiply those things together, I get 44.1 joules of gravitational potential energy. How much work did I do? Okay. It now has 44.1 joules of energy. In order for it to have gained that much, it's because I did 44.1 joules worth of work. Okay, to change, remember, work is a change in energy as well as force times distance. Okay, so work being a change in energy, okay, well, the potential energy it had on the ground was 0. Okay, so essentially, remember, change always means final minus initial. So what I did was take my m times g times h final and subtract m times g times h initial, which was 0 anyway. Okay, that's why it came out to 44.1 joules. Okay. All right, second example. This one's going to require us to manipulate the equation, which is really easy because they're all multiplied together. Okay, I have a 55 kilogram diver standing on a diving platform. Where they are, they have 5.4 times 10 to the 3, that's supposed to be up here, okay, times 10 to the 3 joules worth of energy. What's the height of the platform? So they gave me EP, they told me he has that much energy, okay, they told me the mass, 55 kilograms, all right, I'm looking for height. Do I know what G is? Always know what G is, it's 9.81. Okay, so I'm trying to solve for H, so I do that by dividing M times G over to this side. Okay, that leaves H by itself. Okay, and now I can solve for H by going energy divided by mass times gravity. When you punch that into your calculator, the bottom needs to be in its own set of brackets. If you don't do it that way, your calculator will do order of operations, which is not the same thing. Okay, so if I go 5,400 and I don't put it in brackets, okay, I get this. 963 meters, which is not how high that diving platform is. That would be a fatal fall, even if it was into a pool. Okay, but if I go 5,400 divided by and then put the bottom in brackets, then I get 10 meters. Okay. All right. Now, in order to do work, we got to exert a force through a distance. Okay? One of the most impressive demonstrations of that is people breaking stuff with their bare hands and feet. Okay? Now, in order to accomplish said feat of breaking stuff, okay, it's not just something you or I walks up to a pile of sidewalk blocks and pulls off. Okay? You don't just walk and go, oh, today I'm going to break 27 sidewalk blocks with my bare hands. All right? Because we would never pull it off. Okay? Our bones are not strong enough. Okay? People who do this all the time, okay, they can accomplish that because they train to do it, and they strengthen their bones by the training. Every time your bones experience an impact, okay, there are microfractures that occur in the bone. okay, that are then repaired by the osteocytes, the little bone cells that live in there. Okay? Every time a microfracture is repaired, the bone gets stronger. Okay? This is why people who are elderly and are starting to get osteoporosis, where their bones get kind of thinner, okay, are always told that they should do a lot of walking and some weight-bearing exercise, because that will cause microfractures, not big fractures, okay, that their osteocytes can heal, and then their bones will get more dense, and that's better for them, because if you fall down and break your hip, that's pretty life-changing actually for an elderly person. Sometimes it can even be fatal. So we want to make sure we have strong bones. Well, someone who's always breaking stuff, okay, is always causing lots of these microfractures. Their bones are going to be way more dense than you or I. Okay? That sort of make sense to everybody? No, it's fine as long as you're training up to. You don't just walk up to 27 sidewalk blocks and go, okay, today I'm going to smash that with my elbow, because you'll go like this and then to the hospital, right? Like we don't want to be in that situation. Okay, so if potential energy of an object is released, the object moves. Okay, because potential energy, at least gravitational, is due to being above the ground, and if you let that object go, it's going to accelerate due to gravity. It'll lose potential energy, but it'll gain kinetic, right? In a case like this, we bring our arm above the object, and we don't just let it fall, because obviously that wouldn't do anything. Okay, but we also propel it down with a lot of force. Okay, so we're letting gravity do some work, but we're also doing some work ourselves, force times distance. Okay, and we get down to there. Now, if you're going to break a whole bunch of pieces of wood or sidewalk blocks, you can see in this picture here, okay, that there's space between all of the pieces. Okay? Why does there have to be space between the pieces? Why can't you just set a whole bunch of sidewalk blocks right on top of each other in a pile and break them? Yeah, there isn't room for it to break. If you set them all on top of each other, you're not breaking 27 sidewalk blocks. You are breaking one individually large piece of concrete, and you ain't doing that. Okay? The little space in between allows the work that you did to be transferred from one block to the next. Okay? If you just transfer energy to one big block, which is what you have, if you just pile them on top of each other, you'll never do it. Okay? You would never have enough energy to break them all. Right? But if there's a little space, there's room for one to crack, and then for it to transfer energy down to the one below and the one below. Okay? All right, so I'll show you here some videos of that. Okay, people. Okay, so listen in here, guys. Okay, so obviously it's possible to do a lot of work, transfer a lot of energy to objects, and obviously then change their condition. Okay, in the case of the brick breaking, whether they're intact or broken. Okay, but we use this idea for all kinds of things. Okay, we use it for generating electricity. We use it for pounding a nail into wood. Okay, when you strike a nail with a hammer, yeah, there's sound. Yes, the nail goes further into the hammer or into the wood. Okay, but there's also some heat that's generated there. Okay, and you can tell that if you ever go home and take a hammer and just a little piece of wood and bang on it a little bit, and then put your finger where you were hitting, it's going to be hot there. Okay, you're turning that energy, that mechanical energy, into sound and heat and deforming, okay, that piece of wood. Okay, all right, moving molecules in a sound wave. Make your eardrums vibrate. Okay, that's how we hear sound. So when the waves from my voice hit your eardrum vibrates back and forth. If I scream at you, okay, then they move back and forth further. Okay, not faster, but further. All right, and then your brain detects how far it moves as volume. It detects how quickly it moves as frequency or pitch. Okay. All right. All right. So any moving object is going to have kinetic energy. Okay, you have kinetic energy as long as you are moving, because kinetic energy is related to this. We talked about this a little bit earlier. Okay, kinetic energy is related to the mass of the object and the speed of the object squared. Okay, it is important to remember that speed is squared in that formula, because it means speed has an exponential relationship with kinetic energy. Okay. So if I go twice as fast, I have how many times more kinetic energy? 4 times more. If I go twice as fast, 2 squared is 4. Okay, if I go 4 times as fast, I have 16 times as much energy. Okay? Everybody with me there? Okay. This is something they should teach you in driver's ed, but don't, so I will. What's the speed limit through a playground zone? They do teach you that. 30, okay? School zone, 30. Here's why, okay? This is the work energy theorem. Work is a change in energy, okay? If I'm driving through a playground zone and a kid runs out in front of me, I need to stop, okay? And I need to do it quickly. But the distance over which I stop is exponentially related to how fast I am going. Exponentially related to how fast I'm going, okay? My final velocity I want to be what? 0. I want to have no kinetic energy at the end of this. So if this is 0, really, what I'm dealing with here is that the work my brakes have to do, force times distance, okay, is equal to the kinetic energy that I have at the instant I hit the brakes. Everyone all right with that idea? Okay, so let's say that we have a 1,500 kilogram car and we're driving the speed limit. Okay, 30 kilometers per hour is, I think it's 8.6. But it's 8 no, it's 8.3. Okay, 8.3 repeating. I grabbed a different color. 8.3 repeating. Okay, meters per second. That's what 30 kilometers an hour is in meters per second. Okay, my brakes can exert a force of, let's say, 8,000 newtons. Okay, so when the brakes squeeze together, okay, onto the rotor, that can exert 8,000 newtons of force to try and bring me to a stop. So I know everything except how far I'm going to travel before that happens. So I want to solve for d. So I'm going to divide both sides by f. Everyone okay with my math there? Yeah? Okay. So distance then is going to be 1/2 mv squared over f. So for this situation, that's 1/2 times 1,500 times 8.3, repeating, squared, divided by the force of my brakes, 8,000 newtons. All right, so if I'm going the speed limit, okay, 0.5 times 1,500 times 8.3 squared, okay, that's on the top, okay, divided by 8,000. It's going to take me about 6.5 meters to come to a stop. Okay, 6.5 meters. Okay, so from my desk to here. That's going the speed limit, 30 kilometers an hour, which for all of us feels really slow. Okay, how much faster than the speed limit do most people go? Like 10, yeah, 10 or 15, right? Because it doesn't, 10 or 15 kilometers an hour doesn't make any difference. It's tiny, right? It's not. Okay? 40 kilometers per hour is 11.1 repeating meters per second. Okay? I know these numbers because I do this demo every year. Okay? It's 11.1 meters per second. So if I substitute that in, I'm only going 10 kilometers per hour faster. So we'll take our 0.5 times 1,500, okay, times 11.1 squared. You're only going 10 kilometers an hour faster, but it will take you nearly twice the distance to stop. Okay, 25% faster, and it's nearly double the distance to stop. Yes, you have to factor in your reaction time into that as well. So however fast you were going multiplied by however long it took you to react is also a part of that. Okay, 11.1 meters, guys, is like the length of this classroom plus the hallway, plus the width of the hallway, for 10 kilometers an hour. Okay, so here's the thing. Okay, here's the thing. This is the part people don't think about when they go 10 kilometers per hour faster. If I went 11.1 meters per second instead of 8.3 through a 400 meter long playground zone, how much time am I going to save? Not much. A second or two. Okay? It's not much. Okay? It isn't worth it. Okay? It's just not. I say that because I have 2 little boys, right? And I like to go home and see them. I don't want to go home and plan a funeral. It's that serious, guys. It's that serious. It's double the distance for that 10 kilometers an hour that was going to save you a few seconds through a playground zone. Okay? Think about that when you're driving. Okay? These are the kinds of things you need to think about when you drive. Driving's a bigger responsibility than you realize. Okay? It's the same with a construction zone, right? That's why speed fines double in a construction zone. And I see people do this all the time. Like, well, where's the construction? Where's the construction? They speed up from 50 to 100. Okay? They just quadrupled the distance it's going to take them to slow down. Okay? If a construction worker steps out into the road, they don't have a chance. Okay? 4 times the distance to stop. Okay? So if you were really stupid and went through this at double, so went through a playground zone at 60. Okay, so we'd be looking at 16.6 then, right? 0.5, okay, times 1,500 times 16.6, okay. Whoop, I forgot to square it. Sorry, do that again. 15 times 1,500 times 16.6 squared, okay, divided by our 8,000 newtons. 25.8. Okay, it's a big deal. Okay, 4 times as far. All right, something to think about. But that's why there's a 30 kilometer an hour speed limit in places where small children play. Okay, because speed is exponentially related to stopping distance. Okay, that is exactly why there's a speed limit that is that slow. Okay, and why the town of Okotoks has reduced the speed limit in most of town to 40. Okay, it used to be 50. Okay, they reduced it to 40. They reduced Southridge Drive, okay, below the Darcy Ranch turnoff there below Milligan Drive, okay, down to 50. Used to be 60. Okay, they reduced all of those because of the number of people crossing the road, okay, and they wanted to decrease the stopping distance. All right, something to think about. Okay, so like we said, kinetic energy is energy due to motion. If I'm talking about a whole object, that's mechanical kinetic energy. Okay, there's also thermal kinetic energy, and that has to do with how fast all the individual particles within an object are moving. Okay, obviously the hotter the object is, the faster all the little individual particles move. Okay, you guys remember that from like grade 8 or 9 science? Okay, so kinetic energy of a moving object, like we said, is calculated using 1/2 mv squared. That formula is also on your formula sheet. Okay. So EK is the energy of the object in joules, M is the mass of the object in kilograms, okay? V is the velocity, actually speed of the object, because direction doesn't really matter here, okay? Speed of the object in meters per second, okay? And that'll again give us kilogram meters squared per second squared, or joules. All right, questions on that? Okay, what we just did here is a typical work energy theorem question for grade 10, okay, where you would be asked to calculate possibly the distance over which a force has to act, or I could ask you maybe calculate the initial speed of the object if I gave you distance and force and mass, basically doing that manipulation. Okay, that would be something that by next week we would be expecting you to be good at. Okay, is setting force times distance, the work, equal to the change in energy, because that's what work is. Work is that change in energy. So we initially started out here with force times distance, okay, equaled our final energy minus our initial energy. Okay, that's work energy theorem. Could it be the same for potential energy? Right? If I lift something up, okay, am I doing essentially the same thing and going force times distance equals m times g times h final minus m times g times h initial? Right? If I'm on the ground, how much potential energy do I have? 0. And then up here I would have some, and that would have to be equal to the work I did in lifting it. All right with that? So we're always going to be setting work equal to the change in energy in the work energy theorem problem. Oh, see there again, there's my example. That's from last semester. I forgot I had that on there. Anyway. Okay. Which has more kinetic energy? Semi-truck at 30 kilometers an hour or a bicycle at 30 kilometers per hour? Semi-truck. Why? Has more mass, right? M is bigger for that one. V is the same for both of them. Okay, this is a weird one. Water doesn't always freeze at 0 degrees Celsius. You can cool it to -20 or -30 and it'll stay a liquid. Okay, it's weird, but you can do it. Okay, you slow the molecules of water down really, really slow. Okay, but you don't allow the crystallization process to happen. Okay, so this water still has the potential thermal energy of a liquid while having the kinetic thermal energy of something that should be much colder. Okay, I had a prof in university who showed us this, and we were talking about the heating curve of water, which we actually go over in the next unit. So he had this container that had liquid nitrogen in it, and then there was a beaker of water inside of there that was -25 or something like that. And he took it out, and he had to be really, really slow with it, because any little jarring or anything like that would cause maybe a bubble or something like that to happen, and then the whole thing would crystallize. So he set it down really, really gently, and then he took a grain, like some salt, between his fingers and went like this, and the instant the first grain of salt hit the water, it flash froze, shattered the glass, and there was a block of ice. Okay, right there. Okay, well, I can't do it. I can't super freeze it. I'll show you some videos when we get to that unit of people doing it. Okay, not of the flash freeze, but of kind of a quick freeze. Okay, but you can, if you don't allow the crystallization process to happen, you can do it. One way to try it at home: get a thing of bottled water, put it in the freezer. Okay, leave it in there for a couple hours, and when you take it out, it should hopefully still be a liquid. Then just give it a quick shake, and it'll freeze. And it'll freeze fast just by giving it a quick shake, letting that bubble go through. Okay, but it needs to remain undisturbed. If someone else opens the freezer, they could cause it to move enough to crystallize. Okay, so you got to leave it where it's going to be cold and undisturbed for a while. Okay. Yeah, we don't need to talk about those ones. Okay. Let's have you guys, well, let's go through this one together as our first example. Okay, I have a rubber band, so I have you write this down. I'll give you a minute to write it down, then we'll go through it. Okay, so one of the big things about a question like this is interpreting the question to know what is having its energy changed. What object do I need to deal with? Because in this question, there's two objects that are having their energies changed. Okay, but I'm going to do work on the rubber band. The rubber band is going to do work on the ball. Okay, and it's asking about the ball. Okay, now we also have to remember that whatever work I do on the rubber band is exactly the same amount of work that's going to be done on the ball. Okay, all right. So what they're telling me in this question first is that I'm stretching the rubber band 0.85 meters. So that's a distance that they've given me there. Okay, 0.85 meters. And they tell me by a force of 60 newtons. Anytime you see N, it's going to mean newtons. Okay, so we've got our force here, 60 newtons. What speed would it propel this 0.125 kilogram ball at? Okay, so we're looking for V, mass. All right, so if I'm thinking about this situation and kind of visualizing it in my mind, I'm stretching back a rubber band, okay? I'm exerting a force over a distance. What am I doing? Work. Okay, I'm doing some work. When I let go of the rubber band can do the same amount of work. Why can it do the same amount of work? Because it's going to exert the same force I did over the same distance. Right? I've stretched it back 0.85 meters. It can only move 0.85 meters. And I stretched it with a certain amount of force. That's how much force it can exert. Okay? So that's going to be the same. The work that I do is eventually going to become what kind of energy? Kinetic. It's going to become kinetic energy in the ball. Okay? Now, when the ball is in the rubber band, how much kinetic energy does it have? 0. Okay? Its initial kinetic energy is 0. But its final kinetic energy is what I'm looking for, because its final kinetic energy has the number they want me to calculate, its final speed. At what speed will it leave the rubber band? So I'm really doing this. I'm really going that work is a change in kinetic energy. That's really what I'm doing here. Okay? All I'm doing is eliminating this, because I know that its initial kinetic energy was 0. It was sitting in the rubber band. It wasn't moving. Okay? All right, we'll go over the rest of that tomorrow. Sorry, not tomorrow. Tomorrow we're doing a lab. Friday we'll go over that. Okay?